Okay, which number would you like me to look at? 21. Okay. So we start off with secant 3 theta over 2 equals -2, right? All right, so the thing that makes these harder than like sine and cosine is obviously the fact that you can't look just right off the unit circle and identify easily where you are, okay? So I'm going to use the same practice that I've been doing, and I'm just going to imagine everything in there in the red parentheses, that's my argument. So I'm not going to touch that or address that until after I've actually figured out what the angle is in general, okay? So really I'm trying to figure out where secant is -2. So I'm going to go around, let's see here. Trying to think of which way would probably be best for you. Remember that secant, I'm just going to put down here, secant, I'll use u instead of theta. Secant of u, if we say that that's equal to -2, so all I'm doing is replacing this argument with u just to make this a little bit cleaner. Secant by definition is 1 over cosine, isn't it? So this is the same as saying 1 over cosine of u is equal to -2. And then what I can do is I can multiply both sides of the equation by cosine of u to get the cosine out of the denominator, okay? And when I do that, it cancels on the left. I will be left with just a 1 over here. On the other side, -2 cosine u. Is that all right? Now, try and get this cosine u by itself, dividing through by -2. So you get 1 over -2 equals cosine u, which is the same as -1/2. All right, so now you've taken the problem and you've changed it from secant to cosine. Make sense? Okay. Now, another way to do this would have been to have just started back up here and said, okay, I realize that that's the reciprocal of cosine. Cosine is the x-coordinate, right? So I'm looking for, if you take the x-coordinate and divide it into 1, in other words, put 1 over the x-coordinate, I should get -2. That kind of makes sense or no? No? And not as much as this does? Okay. Since secant is the reciprocal of cosine, I can go around my unit circle looking at x-coordinates. If I flip them, I need to get -2, which is the same as flipping this and getting -2. So I'm just trying to show you multiple ways of viewing it, all right? But it all results, basically comes down to figuring out where cosine is -1/2. So that occurs in 2 places, right? It's up here, and then another one down here. And the angles that correspond to those are what? In 4 pi over 3. All right, since those 2 angles are not directly across from each other, to get my general solution, I'll have to add full rotations to each one of those. So now I'm ready to bring my argument in. For those of you just coming in, I was asked about a homework problem. I'm trying to do it before I start class. Take my argument, which is 3 theta over 2, right? I'm going to take that argument. I'm going to set it equal to my general solutions. So 2 pi over 3, but we said plus 2 pi k. And then the other one was 3 theta over 2 is equal to 2 pi over 3 plus 2 pi k again, because there was no way around having to do them both. Are we good up to that point? Okay. Now it's just a matter of taking each of these and solving for theta. So I'll take the first one here, solve that for theta. So I'll multiply both sides by 2 first. Again, the way you do this is not necessarily, doesn't have to exactly be what I'm doing, but I'm multiplying this by 2 to get rid of the half on the bottom. So that'll give me 4 pi over 3 plus 4 pi k. So that's multiplying both sides by 2. And then dividing both sides by 3, I get theta is 4 pi over 9 plus 4 pi k over 3. And I have to do the same exact thing to the other side. Wait, hold on. Do you see what I did wrong here? This was 4 pi over 3. On my second one, I'd put 2 pi again. Oops. 4 pi. Just change that. They were the exact same thing, right? Yeah, so I'll do that there. Do you realize this one, though, you do the same way, right? Okay, so let me just do this one then. I get a common denominator, so 4 pi over 9. And then I have to multiply top and bottom here by 3 to get my common denominator, so I get 12 pi k over 9. Putting those together, 4 pi plus 12 pi k over 9. That's my general solution. And it's really been, cleaned up. We put it together. This is ready for us to start cycling through with k's. So if you let k be 0, you get 4/9 pi. Getting the secant is -2, like figuring out where that is? Okay. So the other one you said was, which one? Something with tangent in it? Okay. Okay, let's look at it. So you have tangent theta over 2 plus pi over 3 equals 1. Now this one turns out to not be so bad because, well, I hope it's not so bad, because when we're saying our argument, right, when we plug in this argument into tangent, we need to get 1. So we know that that argument, there's really only 2 places tangent can be 1. Are you comfortable with tangent being 1, like understanding that that's where your y and your x coordinates are the same? Okay, so, and it's got to be in either the quadrant 1 or 3. So you're looking at 45 degrees or pi over 4, and then this one over here. They are directly across from each other, right? So I can say my argument, the theta over 2 plus pi over 3, must be equal to, now what I recommend you do is always start with your smaller of the 2 angles. So I'm going to start with this one, pi over 4 plus 2 pi k, or no, not 2 pi k, plus what? Pi k. So this right here is this solution, pi over 4. Adding pi gets me this solution, and then adding another pi gets me back here. So I'm adding multiples of pi instead, 2 pi. And now it's just solving for theta. So what I'm going to do is I'm going to subtract pi over 3 from each side. And notice that when I do that, I have to combine like terms, so to speak. Like pi over 4 and pi over 3 are both like terms because they don't have a k in them. I cannot subtract pi over 3 from this because it doesn't have a k. So I need to figure out what this is. Maybe I'll do that over here. Pi over 4 minus pi over 3. I have to get a common denominator to subtract those. So 12 is my common denominator. Then you get negative pi over 12. Is that what you got? If you did that part? That's what you'll get. All right, so let's see, it's 3 pi over 12 minus 4 pi over 12. And when you subtract 3 pi, take away 4 pi, you get negative pi over 12. So here's where we are. We've got theta over 2. If you're coming in just now, I was asked about a few homework problems, so I decided to go ahead and start a little early. And I'm recording this, so if you want to go back, you can watch this later if you need to. So you subtract, and then we're here, right? Now just get theta by itself, so multiply both sides by 2. So you get theta equals, see, when I multiply this by 2, it's going to become 2 pi over 12, which is actually going to be negative pi over 6. So it reduces. And then plus 2 pi k, like that. And now I have to start letting k, oh, well, do you want a common denominator now? I mean, yeah, okay, so you put this over 1, right? So it'll be theta equals negative pi over 6 plus multiply 6 on top and bottom, 12 pi k over 6. So theta equals negative pi plus 12 pi k, all of this over 6. Okay, so now what we do, wait, it only had what? Yeah, we should have, see, because do they want the general solution? They don't want the general solution. They want the solutions between 0 and 2 pi, right? So if we let k be 0 here, then what would happen? We would get negative pi over 6, and that's not within our interval, so we throw that out, right? K is 1, we get, what? Negative pi, and then there's 12 pi here added, so 11 pi over 6. And 11 pi over 6 is within our interval, right? Because 11 divided by 6 is smaller than 2. And if we let k be equal to 2, we get 24 take away 1, so we get 23 pi over 6. That's too big, so we're outside that interval. Do you see what happened? Yes? Okay. So this was our only solution. No, okay, so you wouldn't have 2 because remember, we covered both of these angles by using pi k. All right, that's kind of the key. If the angles are ever directly across from each other, we want to use pi k instead of 2 pi k, because then you don't have to have 2 sets of general solutions. You could have done it, though, and you should have still got the same answer. It's just a little more work. Okay. All right, I have a little handout for you here. It's nothing fun. It's just some stuff we need to talk about for the exam. I'm going to put multiple copies at each table just in case people kind of trickle in here. There you go. Okay, so I know you can all read, but what I need you to do is first thing, put your name on the top of this so you don't forget to do that. Just real quick, write your name on the top. I've been thinking a lot about your exam 3 and how to handle exam 3. So I finally made a decision that I'm going to keep it on the date that it was on the schedule, originally on the syllabus, which is unfortunately the day before Thanksgiving. And there's a couple of reasons why. We don't need to get into it, but in my experience, after Thanksgiving, pretty much everyone's already like kind of shut down. We only have like, after Thanksgiving, we have 2 class meetings, and then we have the next week after that is finals. So I did not want to give an exam the day you come back from Thanksgiving when everyone's still trying to wake up, you know, and I didn't want to do that. And so I decided the best thing for us would be to take the exam the day before Thanksgiving, but because I know people travel and have made plans to, you know, drive to Houston or whatever it is, and they like to leave the day before, I know historically people won't show up. Some people won't show up for the day before Thanksgiving. So what I'm doing is I'm giving you options. You can either, you know, there's what, A, B, C, D, E here. You can either come take it on Wednesday, be done with it, not have to worry about it, or you have to take it either that Monday or Tuesday that we come back, and you have to do it on my time, not during class. So if for some reason, I want to see if you can fit these times into your life. If they don't, talk to me. But if you know you can't make any of these times, you need to circle E. All right? And I need this back to me by next class, right? That's what I said? Please select an option below and turn it into me on Wednesday, November 19th at the beginning of class. Now, if you know right now, you can turn it back into me today. But if you need some time to think about and figure out things with your family or whatever, then you do that, all right? Does that sound fair to you? I mean, I'm trying to be fair, but not okay? All right. If you do wind up circling option E, then I'm going to want to talk to you because I want to see if there's anything we can do to work something out. But it comes down to fairness, all right? I can't give a test next Wednesday and then let someone else take it like a week and a half later. You know, it's just not fair to let someone have that much more time to take a test. And also, if you take it, if you don't take it on Wednesday, if you take it later, it won't be the same test. I mean, it's going to be a different version of the test. So, all right. We last class we were talking about these identities, right? And I had done this one. I don't think I assigned any homework out of this, did I? Or I did, but I said good luck, you know. All right. So you need to see more examples of this. That's what I'm going to spend time on. So I'm going to pick up 8.4.4, but I am hoping that all of you were able to get through most of the solving equation problems. If you're having trouble on those, please get with me, go to the tutoring lab, do something. Don't just assume that it's going to go away. All right, so today all we're doing is continuing 8.4 and hopefully getting into 8.5. We'll talk about the test as, you know, as we need to. Okay, show this is true. Show that secant theta, cotangent theta, did I do this one? Hold on, I didn't do this one. Hold on, did I do that? No. Okay. The last problem I did was sine squared v. Sorry. No, I'm off on my notes here. I apologize. I did. That was my last one, correct? From last class? Yes, that was it. Right? Oh, well, yeah. I'm on the wrong page here. That was it. That was the last one I did. Okay, so I need to change. This is 8.4.4, so I'm on 8.5. 8.4.5. Okay, so we want to not show. We want to simplify this. Sine squared v minus 1 over tangent v sine v minus tangent v. So I want to simplify this. This is not the same as proving an identity. An identity, they give you an equation, right? And you have to start with one side and make it turn into the other side. When they just give you an expression, all you're asked to do is simplify, then you just need to try and make this, I guess, easier on your eyes. It's kind of nasty looking. You want to make it a little nicer, right? So anybody see anything right off the bat? I mean, these are things I can't really teach. I mean, you kind of have to kind of see it, and you know, maybe I show it to you one time and you kind of get it, but anything that you can do algebraically here. Is this the same as cosine squared? Okay, is it? What do y'all think? So you're seeing the 1 in the sine squared, and you're starting to think Pythagorean identity, right? That's perfect. I mean, that's the way you want to think. Let's just take a look at the Pythagorean identity real quick. I'll replace my angle with v just so it kind of matches what we have. That's our Pythagorean identity. Is there a way that you can write it so that it's sine squared v minus 1? Well, could I move the 1 over here? And it would be minus 1? But then that cosine squared would need to go to the other side and become what? Negative cosine squared. So I do agree that I could rewrite sine squared v minus 1 as negative cosine squared v. Does everyone agree with that? Okay, I could do that. Anyone else see anything? Sorry, excuse me. I'm not saying that's not the way to do it. I'm just asking. Anyone else see anything we could do? How about the denominator? You see anything on the denominator? I want you to start thinking in terms of factoring, okay? Try and think about things that you do when you factor. In the denominator, you see anything here? How many terms do you have? You have 2 terms, right? They both have tan V in them, don't they? So could I factor a tan V out here? Yes? If I did, so this is kind of a separate thought over here, I could pull a tan V out of the bottom, and what would I be left with if I pull a tan V out? Sine V minus 1? Isn't that what I would have if I pulled a tan V out of the bottom? These are just my thoughts, right? These are the things I'm thinking about, you know, things I could do. Now, take a look at this for a second. If I pull that tan V out, I'm left with sine V minus 1. That's very close to what I have here, isn't it? Except that this one was squared. So now, now that we're thinking about it again a different way, do you see something here other than the Pythagorean identity? Do you see something else? A difference of squares. Difference of squares. Remember difference of squares formulas from college algebra? You know, x squared minus a squared is x plus a times x minus a. We could do the same sort of thing there, and I could rewrite that as sine squared v minus 1 could be rewritten as, what, sine v plus 1 sine v minus 1? Do y'all see that? Now, why is this good to see this? What would happen if I replace the top with this and the bottom with this? The sine v minus 1s would cancel, wouldn't they? And that'd be a good thing. So that's the avenue, that's the route I'm going to take. Now, had we switched it to cosine squared v negative, we may still get there. It's probably a different route, but we would probably get there. So I'm just trying to take you on what appears to me to be the most direct route to get to the solution. So sine v plus 1, sine v minus 1 on top, factoring difference of squares. On the bottom, just a regular old factoring of a GCF, greatest common factor. Now we have these factors cancel, right? And we are left with sine v plus 1 over tangent v. Oh, just tangent v. Anything else we can do? Yes, I could. Then what, like multiply the top by cosine, or not sure what? Okay, so I guess the question right now would be, do you think that that's simple enough? You know, because you were supposed to simplify, right? And if you were taking a test and you did this much, I would definitely give you credit for this because you've done some simplification. We could argue, could it go further? So I think you see that the tangent v could go to a sine and cosine. Maybe something nice will happen. I'm going to see what happens, all right? I'm kind of seeing it a slightly different way, though. I do agree about the changing to sine and cosine, but because I have 2 terms in the numerator of a fraction and 1 term in the bottom, can't I split it into 2 separate fractions like this? Right? If I have 2 terms up top, 1 on the bottom, I can split it into the sine v over tan v, and then the 1 over tan v. I can do that, right? It's a legitimate move. The only reason I like that is because what's 1 over tangent? Cotangent. That's just going to turn to cotangent right there. So I like that. I just need to resolve what this is. So I think that's where you might want to switch things to sine and cosines. So I have sine v over tangent v, which was sine v over cosine v. And then plus, what did we say 1 plus tangent was? Cotangent v. Did we talk about the division? We did, right? About how it's important to know which is the major division, the kind of minor division. So this is what's happening. What happens when I take this and flip it up to that one? The sine v on top is really a sine v over 1, right? That's what this top one is. And I take this fraction, I flip it up and I bring it next to this. So it would be cosine V over sine V, like that. Over here, I still have plus cotangent V. Anybody have any questions on what I did from here to here? These are those little subtleties that you have to be comfortable with in your manipulation of fractions. Sines will cancel, won't they? And you just get cosine V plus cotangent V. I think, would we all agree that that's probably as simple as we want it? Be happy with that? All right, so this problem involves some factoring techniques and then simplification after that. Let's go to our next example. 846. So now we'll do that one. Show, that means this is an identity. Secant theta cotangent theta equals cosecant theta. This one is rather straightforward, but because we're being asked to show, we need to make sure that we are doing it properly. So I said last class, if you're asked to show an identity is true or show equality always holds for something, then that means you always have to start with one side and turn it into the other side. And which side did I say to try to start with? Do you remember? The one that looks more complicated, all right? See, it's very difficult to start with something like cosecant theta and say, oh, that turns into what? I mean, you see, it's already so simplified. Where do you take it from there? So if you start with the one that's more complicated, there's a lot more you can kind of think through here, a lot more things you can do. So I'm going to start here, secant theta, cotangent theta. This is my left-hand side. I'm going to start with my left-hand side. I'm going to try and at the end get the right-hand side. So what do you think? Okay, turn secant into 1 over cosine. Turn cotangent into cosine over sine. Is it that simple? That's it. That's just 1 over sine. That is cosecant. So you probably just want me to give you like 30 of those. Call it a semester, right? All this problem really was here for was to illustrate again, you start with one side, you have to get it to turn into the other side. That's the proper way. What would happen on an exam if you did this? 1 over sine theta, 1 over cosine theta. I shouldn't even write this up here. Cosine theta over sine theta equals 1 over sine theta. And then you came in and you multiplied both sides of this by sine theta. You started doing things like this, right? This sine cancel, this sine cancel. Then what are you left with? Cosine theta over cosine theta, which is what? These cancel, so you get what? 1 equals 1, and so you say check, that's true. What happens if you do that? You get no points. Because the problem is you showed that you verified that it was true. You verified it, but you didn't show it was true because you worked with both sides of the equation. You cannot do that when you're trying to show an equation's true, right? You have to start with one and manipulate it, transform it into the other side. If you work on both sides at the same time, then you're assuming it was true to begin with, which goes against what you were trying to show, right? Okay. No. That's the good thing about identities, is that they're always true. It's a matter of can you get it to, left-hand side to right-hand side. As this next example might illustrate, it can be a little more challenging. 847. Yeah, that'd be just cruel. Where? Over here? You would go 1 over sine equals cosecant theta, and then you'd say, you know, that's the right-hand side. Is that what you're asking? No, it's like a bridge. You're trying to get from one side of the bridge to the other side of the bridge. The left-hand side, your work is the bridge all the way over to the right-hand side. You totally ignore the right-hand side, and at the end of your work, this better be your right-hand side. Yeah? Okay, look at this one. Show that sine squared negative theta minus cosine squared negative theta over sine negative theta minus cosine negative theta equals cosine theta minus sine theta. That's a pretty nasty looking identity, right? So to show that this is true, I forgot to put show up here. Show that that's true, we need to turn one side into the other. And it doesn't always have to be the left-hand side to the right-hand side. Sometimes you start with the right-hand side and go to left. I think in this problem, we might agree that the left-hand side is a lot uglier than the right. So we should probably start with that one. So what if we have left-hand side here? What are some of the things that are going to lead you to the answer? I mean, what are some things you start looking at? Well, one thing I see is that my answer is all in terms of theta, isn't it? Like, look, I have cosine theta, sine theta, but my left-hand side is what? Negative theta, negative theta, negative theta, negative theta, right? So we're going to have to turn all these negative thetas into theta somehow, aren't we? But remember we had what we called the even and odd property of sine and cosine? Remember that? We did that, I believe it was last class. It's all kind of blending together. See where we're, or even and odd. I don't know. They're in there. I'm not going to go look them up. Even and odd. So what the even and odd identities said, and I'll just write them on the board. It said sine negative theta was equal to negative sine theta. And then, oh, these are on your formula sheet too, right? Okay, cosine negative theta is equal to what? Just cosine theta. So what I'm getting at is there are ways to transform our negative thetas into thetas. So let's do that first. Do y'all think that's a good idea? I'm going to start with my left-hand side. How can I rewrite this top left corner using the identity? I can replace the sine negative theta with negative sine theta, but then what am I going to have to do with that after I replace the sine negative theta here? Square it, right? The squaring comes after. So watch the way I write this. I'm going to switch that sine negative theta into negative sine theta and then squared. So I'm changing the notation of this a little bit just to kind of help us see what's going to happen. Is that all right? Good? All right, minus. Now, what does the cosine negative theta become? Just cosine theta, right? And then I'm going to square that all over what happens down on the bottom here. Sine negative theta turns into negative sine theta, right? And cosine negative theta turns into what? Just cosine theta. Does everyone agree? All I've done is I've used the even and odd properties of sine and cosine to rewrite that. Now I'm happy because at least everything has theta in it, and that's where I'm trying to go. All right, now let's just clean this up. What happens if you square negative sine theta? The negative out front is really like a negative 1, right? So if I square negative 1, what do I get? Positive 1. If I square sine, what do I get? sine squared, right? So look, the top left is going to turn into sine squared theta. And I don't need the negative because when I square it, it's gone. Make sense? How about this one? Cosine theta, when I square it, it's just cosine squared theta, right? The minus in the middle here is not affected, right? The subtraction is not affected by the squared because it's not being squared. The minus was never being squared. It was just separating our terms. So I'm still going to have subtraction here. All over on the bottom, can't really do anything, can I? Well, it depends on how you want to look at this. Does anyone see where this is going to go? Anybody see the numerator over there, what we have? I know you're probably thinking Pythagorean identity, maybe. But what else could we look at that as? We just did it in the previous problem. Difference of squares again, but this time it's sine squared minus cosine squared. So what could this turn into? And I'm doing this mentally, all right? What's sine squared theta minus cosine squared theta going to turn into? Sine theta plus cosine theta times sine theta minus cosine theta, right? And I'm hoping for cancellation. This is not going to cancel because they both have negatives, don't they? Why don't I factor a negative 1 out? Why don't I do this? Pull a negative 1 out, and that would leave me with sine theta plus cosine theta. Has anybody here ever done anything athletic, like running a marathon or swimming long distance or anything? Anyone ever done any sort of endurance sports? No? That's the first thing that comes to my mind, I guess. Has anyone ever rode a bike? Yeah? Okay. When you first ride a bike, right, they don't just put you on the bike and then take you to this really hilly place and just push you down the hill. Well, my dad kind of did that, but you don't get on the bike for the first time and then go to a dirt track and try and do tricks, right? That's just not the way it works. There's always a slow progression into it, right? You get more comfortable, Same thing here, okay? This stuff comes with time and experience, but I can't teach you time and experience. That has to happen at home, trying the problems on your own, running into roadblocks, trying something different. You may have tried the Pythagorean identity here and just run into a dead end. I just can't illustrate enough to you or stress enough to you how much of this is trial and error. Try something, make a mistake, try something, make a mistake. Eventually, hopefully, it happens. All right? So I'm recognizing difference of squares up here, right? Because I've been riding this bike for a long time. I see difference of squares, and I see it's going to be down here, and I see it's going to cancel. All right, so here comes the top. Sine theta plus cosine theta times sine theta minus cosine theta. Then all of this over negative 1 sine theta plus cosine theta, like that. Do you see how if I had not taken the negative 1 out, these wouldn't have canceled, right? They wouldn't have matched up. So I had to see that negative 1 pulls. And then now I can cancel the positive ones, right? These two cancel. And that leaves me with what? Sine theta minus cosine theta over negative 1. Is that my right-hand side? Yes, but I need to change a little bit, right? Remember, having a negative on the bottom, you can just, well, there's so many different ways you could look at this. I could split this into 2 fractions, couldn't I? What's sine theta over negative 1? Negative sine theta. What's negative cosine theta over negative 1? Positive cosine theta. So, this is going to turn into this right now on the next move, and I'm out of space. This is negative sine theta plus cosine theta, which is my right-hand side, so I am done. Questions? I want to illustrate some of the difficulty here. I want you to try one, because watching me, what's the point sometimes, right? Try this one. 1 plus tangent theta over 1 plus cotangent theta equals tangent theta. Okay, I want you to show that. So let's see what you can do. I'm going to walk around and see how many of you are getting stuck, how many of you are trying something. Work all these problems in class, right? Unfortunately, that's the way pre-cal is. So I'm going to go about it the way that everyone seemed to have done it, and then I'm going to show you a different way, all right? So it seems like most of you wanted to take the left-hand side and rewrite it as sine theta over cosine theta here, and rewrite the bottom one as the opposite, cosine theta over sine theta. I should say the reciprocal. And then you get the common denominator here, and when we do that, you get cosine theta plus sine theta over the common, which was cosine theta. What would the denominator fraction be? What would these two together be? Sine theta plus cosine theta over sine theta. Is that all right, everyone? And now you have, see, the whole idea of this is that now you have a fraction over a fraction. Instead of, well, here we had a fraction over a fraction, but we had like 2 terms here without common denominator. So now what we'll be able to do is take this fraction and flip it up there, right? When I flip it, the sign goes on top, and then the top becomes the bottom, right? Like that. It's gone from there. And now we're multiplying straight across. So do you see that these two factors are exactly the same? And they cancel each other out. So since they cancel, the only thing that's left is what? Sine theta over cosine theta, which is tangent theta, which is the right-hand side, which is what we wanted to show. I think I'll just let it be. I don't want to show you another way and then get you all confused. So let's just let it be with that, all right? Next one. Let's show, let's see, that one was 8. That was supposed to be 848. So the next one is 849. How about show sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta equals 2 cosecant theta. Which side should I start with? Left, right? Left-hand side. So there's my left-hand side. When I was walking around, I noticed that some of you were still bringing your right-hand side down here. Leave your right-hand side alone. You can't mess with that at all. That's what you're trying to end with, all right? So there's my left. Any ideas? the last problem, we turned our sine and cosines, our tangents and cotangents into sine and cosines. A lot of times when you get stuck, that's a good thing to try. Just turn everything in terms of sine and cosine. But in this problem, they're already sine and cosine. So you can't really mess with that. So common denominator. Okay, so you see that we have two fractions. So why not try and put them together, right? Why would it be wise to think that? Well, our final answer is just one term, isn't it? Just one thing. And right here we have two terms, and they're rather complicated looking. So if we try and get them into one, at least we know that we're maybe headed in this direction. So a common denominator here would be 1 plus cosine theta and the sine theta, right? Those are our two denominators. So on the first fraction over here, I need to introduce what on the top and bottom here to get a common denominator between these two? What do I need here? Sine theta on top and bottom here. Now I'll do it in red so you can see I'm bringing in sine theta here and over sine theta here. So that's the part of the common denominator that's missing on this fraction. What do I have to add or multiply in over on this side? 1 plus cosine? Yes? So 1 plus cosine theta on top and bottom. Now I put the 1 plus cosine theta here in parentheses. I did not put the sine in parentheses. Why did I put this in parentheses and not this one? I just like parentheses. How many terms are there here? There's two of them, right? 1 plus cosine theta. There's two terms, so when I multiply it, it's going to have to distribute, so I have to be careful with that. In fact, look it up here. When I multiply these two together, I should actually put these in parentheses also, because this is two terms times two terms, binomial times binomial, so I'm going to need to do that whole FOIL thing, right? Are you all ready to multiply this out? Sine times sine on top would give me sine squared theta. Then I have the plus sign, which was in the middle of the two, is now going to be right here. And then let me actually multiply this all out. What's 1 times 1? 1. 1 times cosine theta, cosine theta. In the middle again, I get cosine theta times 1. So I'm going to have how many cosine thetas there? 2 of them, so I'm going to put plus 2 cosine theta. And then what's my last multiplication? Cosine theta times cosine theta. Cosine squared theta is the way I write that. All over, all of it, right? The whole thing over sine theta times 1 plus cosine theta. I did not multiply that out, all right? I did not multiply that out. Why didn't I? I don't know. Maybe again because I've been on this bike for too long. No, it's because, look, what is cosecant theta? It's 1 over sine, isn't it? I have my sine down here already. I have a sine by itself, right? If I can get this to go away, and this is here, then I have that sine on the bottom. Can you grab the door? Do y'all see that? So I'm not going to distribute the sine through and further complicate the issue. I'm going to leave it here. Do y'all see what great things are going to happen up top? I don't know if they're great things, but they're nice things, okay? This one should just hopefully pop out and almost bite you. What's sine squared theta plus cosine squared theta? 1, right? That's the Pythagorean identity. Sine squared theta plus cosine squared theta, if I put those side by side, that should be 1, right? So this is a 1, and then I have what here? Another 1, so what's 1 plus 1? 2. So you're telling me that this turns into 2 plus 2 cosine theta over sine theta times 1 plus cosine theta? That's what it turns into? What are we supposed to have up there? 2, right? Cosecant theta. I see a 2, but it's in both of them, right? And then here's my cosecant's going to come from this. This is not a good thing, the 1 plus cosine theta. So do y'all see what I can do? Take a 2 out. Factor GCF a 2 out of both of these. There's two terms there. If I do that, I have a 2 comes out. What am I left with on top? 1 plus, oh man, are you serious? 1 plus cosine theta all over sine theta times the 1 plus cosine theta again. And do you see they're gone? And now we have 2 over sine theta, which is 2 cosecant theta, which is my right-hand side, which makes me happy. It's a big puzzle, all right? That's all it is. It's a big puzzle. You're trying to use your identities to try and make things work out. Okay, yeah. So it is 1 over sine. Let me show you something here. When we were left with 2 over sine theta, right? This is the same as 2 over 1 times 1 over sine. You have to agree with me on that first. Do you agree that these two mean the same thing? Because multiplication of fractions is straight across. 2 times 1 is 2, 1 times sine is sine. So if I rewrite it this way, 1 over sine is cosecant, and 2 over 1 is 2. So that's 2 cosecant theta. Yes? Nice one. Y'all doing okay? All right. How about this one? 8.410. I want to show this. I want to show that 1 minus sine theta over cosine theta is the same as cosine theta over 1 plus sine theta. So which side do you want to start with? Which one looks more complicated? They're about the same, wouldn't you say? I mean, they're almost the same. So this is one of those situations where you just got to pick a side and just go with it, all right? Just go and see what happens. So I'll let you pick. I worked it a certain way. I'll let you pick. Which side do you want me to start with? You want me to do left? Okay. Left-hand side. It's 1 minus sine theta over cosine theta. Now what do you want me to do? Tell me if I could do this. Tell me if this is okay, and just think about this. Don't necessarily write this down. Could I rewrite this as 1 over cosine theta minus sine theta over cosine theta? Could I do that? And then rewrite that as secant theta minus tangent theta? Is that true? 2 terms on the top here, 1 on the bottom. I can split it into 2 fractions, can't I? So that's legal. This is okay? Now, should I have done that? Has it taken me to the answer? I'm definitely not there, right? Can you split this one into 2 fractions? No, right? You cannot. If you have 2 terms on top, 1 on the bottom, you can split it. If you have 1 term on top, 2 on the bottom, you cannot split it. Are we all comfortable with that? This is like fraction stuff. You have to be comfortable with that. But if you're not, you know. This class is so difficult to gauge. I told you it's so hard. Nobody wants to talk to me in here. I have no idea. Okay. What are both of those equal to? What are both of those equal to? 1, right? Those are both equal to 1? All right, let's try and see if I'm allowed to split this up into 2 fractions over here. 2 over 5 plus 3 over 5. What's 2/5 plus 3/5? 5/5. 5/5 is 1. So it makes sense that that would be true. Can you split this into 2 fractions? 5/2 plus 5/3. 5 divided by 2 is 2.5 plus something bigger than, this is like bigger than 3, isn't it? Which can't possibly be 1, can it? Do you see what I'm saying? I'm just trying to show you with an example how you can convince yourself whether or not you're allowed to do this or not. This is not okay. I think when I was a student of math early on, I had trouble remembering what I could and couldn't do, and anytime I had trouble, I always wrote down an example to try and figure it out myself. To eventually I got to the point where it was automatic. So I'm just encouraging you, trying to explain that, look, you may not always remember all the rules, but you can't just guess. You can't be like, yeah, I think I can. You have to either look it up or you have to do something and convince yourself it's true. All right, so I'm getting off on a tangent here. Has this helped me? No. Right? This has not helped me because I've taken it somewhere where I'm not even really close to this. So maybe something else. Multiply the top and bottom by what? What? Are you crazy? What are you on over there? Why? Why in the world would you do that? I mean, like, yeah, look, so taking this expression and multiplying the top and bottom by 1 plus sine theta, which doesn't make a whole lot of sense, except for the fact that in our answer where we're trying to go, we want a 1 plus sine theta down there, don't we? So why not introduce it on the top and bottom and just see what happens? And good things do happen. Right? So that seems like a very, just crazy step, but it's what's going to get us there. All right, so I'm going to FOIL out the top. 1 times 1. 1 times sine theta. Negative sine theta times 1 is negative sine theta. So the middle terms cancel. And then your last terms, negative sine theta times positive sine theta, is negative sine squared theta. All over what? Just leave this one alone, right? Now, has that helped? I have the 1 plus sine theta here. Yay, I'm happy about that. But I also have this thing that's ugly up here, and I have this down here. I'm not happy about that. But what is 1 minus sine squared theta? Cosine squared theta from the Pythagorean identity, right? So by the Pythagorean identity, the numerator becomes cosine squared theta over cosine theta, 1 plus sine theta. And do you see what happens now? This 1 minus sine squared theta became cosine squared theta by the Pythagorean identity. And now the cosine squared theta over cosine theta, one of the cosines cancel on top. So one of those is gone, so it's not squared anymore. And then this one went away. So you are left with cosine theta over 1 plus sine theta, which is the right-hand side. All right, your homework, in case I didn't write it down, I think I did though, was 19 through 63 odds. Is that what I had put down? There's a lot of work there. One of the most difficult homework assignments you'll have, because you can't check the back of the book because you're trying to prove an identity. You already know the answer is there. You just have to get to it, right? So it's one of the most difficult homework sections in the book. And actually in pre-calculus altogether, this is one of the most difficult concepts. Students don't tend to enjoy identities. All right, I'm going to take maybe 5 minutes. I want to just share something with you because, you know, I've had lots of conversations with people lately and about, you know, what's the value of you know, pre-calculus, or what's the value of getting a degree, you know, versus just not, right? Like, what does it really mean? And to me, what I'm hoping you gain from an education is problem-solving skills, the ability to solve a problem. These are problems that you're trying to solve, right? It's a matter of can you navigate through this thing and get to a solution. So I wanted to share something I did this weekend that turned out to be a problem-solving exercise. Just to give you an idea of what engineers, how many of you are like engineering majors? And, okay, computer science. What else do we have in here? Biology, right? Chemistry. Okay, everyone here has some field that's somewhat related to math in some sense, and most of you will be doing problem solving in some respect, right? So I have an 11-year-old stepdaughter who has a science fair project, right? So I said, you know, let's talk about, you know, what do you want to do, whatever. So she was interested in, if you take, and this is because I had talked to her about it before, but if you take a gun and you aim it horizontally and you shoot a bullet out the gun, it takes a certain amount of time for it to hit the ground, right? The bullet will eventually hit the ground, yes? Well, her question was, if you shoot a bullet out of a gun from a certain height and somehow figure out how long it takes to hit the ground, and then you just drop a bullet from the same height without shooting it out of the gun, which will hit the ground first? Which takes longer, or which hits the ground first? Either way, right? Understand the question? So what do you all think? Same time? So it doesn't matter that that one's been shot out of a gun at 1,000 feet per second? Both bullets will hit the ground at the same time? So you have your own ideas, right, of what you think will happen. So we ran an experiment, right? And we got a Nerf gun. We set it up on a tripod. And the challenge, okay, this was the problem-solving part of it. The challenge was to try and figure out how we could get a good measurement of time, right? Because we're going to shoot this Nerf gun. We needed to somehow be able to start the clock there, right? And we don't have, like, I don't have expensive calibrated instruments at home to do this, right? I'm just what we got at home. That's all we had. So how are we going to measure, start the clock exactly when we pull the trigger, and then how are we going to stop the clock exactly when it hits the ground, right? So in all of the different discussion that we had about it, what it came down to is using technology that we all have in our pockets, our phones. So what we did was we shot a video, okay? And so the gun's right here, and we shot a video that shows the dart. You know, we're running the video and then say, okay, shoot. And then it shows the dart, you know, will come out, right? And then the camera's still here, and then what happens? Later on, you actually hear the dart hit the ground. We did it in our house. It's very quiet, you know. We hear it hit the ground. So what we did was we uploaded that video onto my computer, and I'll just show you the picture real quick so you can see what I'm talking about. Okay, so there's the actual, this is the picture that we're going to put into her project. So she's taking the video, I'm shooting the gun, here's the gun, I've mounted it to a tripod, and we're shooting it out, and I uploaded the video to this software, and look at this. Okay? We're able to, this is our timeline for the video, we are able to figure out where we look at the video to where the dart leaves the gun, right? So we know where to mark the time, and then we listen. That's when it hit the ground, and we were able to measure that time. Does that make sense? That is problem solving. Does that make sense? It's like nobody sat there and told us, okay, this is the way you should do that. I mean, we just used what we had and we solved the problem, right? We did 10 trials. We computed the time for each of the 10 trials. We took an average and we figured out how long it took, right? Then we did the same exact experiment, but just dropping it, videotaping the drop, listening to it, right, 10 times, and we compared them. And when we got the final results, we were able to determine that the dart shot took 0.03 of a second longer than the one that we dropped. Okay? You all with me? Now, theoretically, it should be the same. So there was a mistake somewhere in there, all right? Anybody know what our mistake was in it? Well, it's not a vacuum, correct? That's one thing. But both of them were dropped in air, so it should be somewhat the same. Remember I said I had the camera right here, right? We shot it, and then we listened for it, right? We listened for it. So when we heard it, is that when it hit the ground? No, because it took time for the sound to get to us, right? And we measured it. It was 37 feet. No, 36 feet is where it was hitting. Sound travels at 1,116 feet per second. That means it takes 0.03 of a second for the sound to get from there to us. So the 0.03 of a second that we were off by was actually the error in the sound. So we were actually, in all of our data, we were off by 1/1000th of a second was how much difference there was, which was negligible. All right? It was a beautiful experiment. I did not expect for it to come out that good. I was expecting, we're going to be off by like 5–10%. I did not expect to be that good with it. But it was a problem-solving exercise. And that's what it's always about. I mean, this is not about, are you going to be able to prove an identity someday? No, but if you get an identity like this and you're just stuck, then how are you ever going to take that problem that's much more advanced and tackle it? You have to get used to thinking through things, trying things, not surrendering to the problem before it's even begun. Does that make sense? I hope so, because that's what I want every one of you to become. That, you want to become the engineer, you need to be able to problem solve. You want to do computer science? Look, coding is not fun. You got to be able to problem solve when you code. So, medical field, I hope you problem solve. Just don't go in and just like my mom's doctor. Antibiotics for everything. Just give me antibiotics. What's wrong with you, Mom? I've got this cough. You gave me antibiotics, I'll be fine. That's not problem solving. That's just throwing that's just throwing stuff at it. All right. I should have stopped my recording. Oops. That was not necessary. All right. Well, the next section, 8.4, or 8.5, thank you. There's really not a whole lot more in terms of this is a brand new topic. All it is brand new formulas. And then now we get to apply these formulas to more problems. So we've had Pythagorean identity, right? We've got the even and odd properties, right? We've got that. So now some more properties. The title of this is sum and difference formulas. All right, so these are formulas that involve sine, cosine, and tangent when you have sums and differences in their arguments. So let me just write them down. These are on your formula sheet. Who has their formula sheet handy? I just want to see where they are. Is it the bottom right-hand corner? Bottom left-hand corner. Okay. The bottom left-hand corner has all of these. On your formula sheet, it uses U and V. Okay. So you should have a formula there that says cosine U plus V equals cosine U cosine V minus sine U sine V. Y'all see that there? And then you've got how many more? You got cosine U minus V, right? Pardon? Oh, they have it as 1. You have to be careful then. Do they have a minus under here like that? And then over here they have a plus. Oh, this is a good opportunity to teach you something about being careful on formula sheets. When you see plus or minus on formula sheets, the order in which they appear is important. Meaning if the plus is on top here, that means that the formula is plus here, and then whatever's over here on top is what's over here. So it's a plus here, then a minus here. Got it? If you use a minus here, then it's a what? A plus over there. Do y'all see that? That's a subtle thing. They don't just do it like flip it just for fun. They flip it because they have to go in that order. So your book does it this way. They actually list out the two formulas separately. And that way there's no confusion on the signs. You just got to make sure on your formula sheet you understand that. All right, that's this sum difference formula. Do you see why they call it sum difference? If you have a sum as the argument or a difference as the argument, you can split it up into this big old nasty thing, all right? And then there's two more for sine, right? Now on yours, it should say plus or minus there, right? And then over here, doesn't it say plus or minus again? So notice on this formula, it's not, they don't switch, right? If it's plus on top, it's plus on top. If it's minus, it's minus. And then what's the formula? Sine U cosine V? How does yours do it there? Is it cosine V sine U? It's cosine V sine U? Oh, that's what I meant to say. Cosine U sine V. Right. Those are your formulas for sum and difference. Does yours include the formula for tangent? Yes? Okay, good. So you have the tangent sum and difference formula. And those are kind of nasty looking, right? Notice on the tangent, the plus and minus, do you see it? There's two of them, right? Let's see. Do you have this? Do you have tangent U, what, plus or minus? And then tangent V over 1 and then minus plus tan U tan V. So if you use a plus here, if there's a plus between these two, it's a plus here, but then it's a minus here. So it's kind of weird. And then if it's a minus, it's a plus. Make sure you follow those. And let's just see, how we can use these. This is 851. 852. Find exact value. Sine of how do I want to do this? Sine of 75 degrees? So 75 degrees not on your circle, right? Now you could get your calculator out, get into degree mode and hit sine 75, couldn't you? Yes? But we want the exact value, right? The exact value means no decimal approximation, which means no calculator. So what we're going to have to realize is that we are going to try, if possible, to rewrite 75 degrees as the sum or difference of two angles we do know, like we do have on the unit circle. And hopefully we're all clear with 75 is 35 plus 45. And those are both angles we do know. And now we have our sum formula, right? We have sine of u plus v. According to the formula, this should be equal to sine u cosine v plus or minus plus cosine u sine v. Right? If we have for the formula for sine, if there's a plus here, there's a plus here. And now just replace u and v with what they are. What is sine of u? That's sine of 30 degrees. Cosine v is cosine 45 degrees. Plus cosine u, which is cosine 30 degrees. Sine v, which is sine of 45 degrees. Wait, could you switch v and u and make it 45 plus 30 instead? Like switch the place, this is 45, that's 30, this is 45, that's 30? Is that what you're... You don't. I think what you're saying is you could have done 45 here and 30 here, right? That would give you the same exact answer, okay? Things would look different here, right? I mean, but it would give you the same value. Good question. All right, so now we shouldn't need our calculator at all. What is cosine of 30 degrees? I'm sorry, cosine. What is sine of 30 degrees? So 30 degrees, sine is the y-coordinate. So this is 1/2. What's cosine of 45 degrees? That's the x-coordinate, root 2 over 2. Plus, what's cosine of 30 degrees? Root 3 over 2. What's sine of 45 degrees? Root 2 over 2. Let's just put these together. We have multiplication, then addition. So let's multiply those two together. So straight across. 1 times root 2 is root 2. Over 2 times 2 is 4. So we have root 2 over 4 plus, what happens if we multiply root 3 times root 2? What do you get? Root, careful, you multiply those. So root 6 over 4, those have the same denominator, don't they? So add up the numerators. Can you put root 2 and root 6 together? Cannot. They are not what we call like radicals. So that's your exact answer. That's your exact answer. No decimal approximation. Square root of 2 plus square root of 6 divided by 4. Now, if you got on your calculator, did square root of 2 plus square root of 6, got that answer divided by 4, it should be the same answer as if you just type in sine of 75 degrees to start. But that's the exact. Questions? All right, how about a slightly harder one? How about tangent of pi over 12? Oh, this is just going to be torture. Tangent of pi over 12. Is pi over 12 an angle on our unit circle? No, right? So how are we going to get pi over 12 from two angles we know? 45 minus 30. So how are you coming up with that? Okay, so you figured out that was 15 degrees first. Okay, that works. How do you figure that that's 15 degrees? So you did a conversion from radians to degrees? That's fine. I have no problem with that. That was something that y'all, I think, did before I came into this class, right? Converting from radians to degrees, degrees to radians. And then what two angles were you talking about? So you're going to say 45 take away 30? Now here the order would matter, right? What we call our U and our V would matter. And what is that according to the formula? Formula for tangent of U minus V is tangent U, right? So tangent 45, then plus or minus? Minus tangent 30 over 1 plus tangent 45 times tangent 30. Does anybody have a question as to the application of the formula here? Everyone's okay with just applying the formula? What is tangent of 45 degrees? Tangent of 45 degrees is 1, right? You're going to 45 degrees on your unit circle. Tangent is the y divided by the x. Since they're the same coordinates, it's just 1. Minus, what's tangent 30? So go to 30 degrees. That's root 3 over 2, 1/2. Take your y coordinate and divide it by your x coordinate. And what would you get? 1/2 over root 3 over 2, right? Reciprocate. What would it be? Root 3. All over 1 plus tangent of 45 degrees, we already said was 1, times tangent of 30 degrees, which we said was root 3. So are we getting 1 minus root 3 over 1 plus root 3? Just leave it like that. Hold on a second. Yeah, this is root 3 over 3. Hold on. That's why I came back to it. Look, tangent of 30 degrees is this over this, which leaves you with a 1 over root 3, which we could write as root 3 over 3 if we rationalize it, but we need to change this. Just change this right here to 1 over root 3, and change this one to 1 over root 3, and we're fine like that. And over here in our final answer, 1 minus 1 over root 3, 1 plus 1 over root 3. I just need to replace all my root 3's with 1 over root 3's. Do you see how it works, though? I mean, as far as how we attack that? Okay, let me see something else here. Show cosine alpha minus beta. I'm going to use some of the variables the book does. Over sine alpha sine beta equals cotangent alpha cotangent beta plus 1. Another identity, right? Any ideas? Okay, so this cosine alpha minus beta, we can maybe apply the difference formula to it, right? The formula we just got in this section. Cosine of alpha minus beta by the formula should turn out to be, so I'm starting with left-hand side, should turn out to be what? What's the formula for this piece right here? Cosine u, cosine v, so cosine alpha cosine beta, right? Plus the opposite of what you see there, sine alpha sine beta. So that's just the formula for that. Everything else on the left-hand side is the same. Now what? How many terms in the top? How many terms in the bottom? 1. Can we split that into 2 separate fractions? So if I take the top left and divide it by the bottom, I get cosine alpha cosine beta over sine alpha sine beta, and then plus sine alpha sine beta over the same exact thing, right? Sine alpha sine beta. So this one on the right is just 1, right? This is just 1. It's the same thing over itself. There's something over itself. And then over here, what's cosine alpha divided by sine alpha? Cotangent alpha. And what's cosine beta over sine beta? Cotangent beta. Is that the right-hand side? So I'm looking at this. Right. There, and then this is just a 1. The point that's being made here is that you can use these double angle. You can use these sum and difference formulas in identities also, you know. Okay, I have maybe one more problem I want to show you. Well, maybe 2. See how much I can do in the next 13 minutes. Let's solve an equation. If you did your homework on solving equations, you know, I guess x is fine. Yeah, we'll leave it as x. If you did your homework on solving trig equations, you didn't run into anything like this. Most of what you did was factoring, right? Things like that, or moving everything to one side, solving for the trig equation or trig function. Problem here is we have both sine and cosine. They're both linear, meaning we can't use a Pythagorean identity, right, to get rid of one of them, turn it into cosines or sines. Can I just set each one of these equal to 1? No, because they're being added together. I can't do that. So you could sit here for a while and just be like, I don't know. So let me just do something and see if you follow it. When you have an equation, you have done this in the past. You've squared both sides of an equation before? Yes? You've done that. So why don't I just tell you come in here and square both sides of this equation. If you square the left side, that means you have to FOIL it, right? Expand it. And then squaring 1 gives you 1. So this is what it means to do sine x plus cosine x squared. You multiply it times itself. You do not just square each one, right? It's a big no-no. You have to do this. So when I multiply through here, I get sine squared x, because sine x times sine x is sine squared x. I get sine x times cosine x. And then again, I'm going to get another one of those in the middle. And then my last term will be plus cosine squared x equals 1. Everybody follow? Understand the foiling there? Do you see the good news? What's that? That's a 1, right? That's a 1. Sine squared x plus cosine squared x is 1. These two here can be put together because they're the same, like terms. So I have 2 sine x cosine x. I had plus 1, that Pythagorean identity, and then I had 1 on the other side. Now that looks more like what you had for homework. Move everything to one side. You get 2 sine x cosine x equals 0. I divide through by 2. And now I have 2 separate equations to look at. I have sine x is 0, and I have cosine x is 0. Where do those happen? Where is sine 0? Where's sine x 0? Sine is the y-coordinate, right? So 0 and pi? Yes? Where's cosine 0? Pi over 2 and 3 pi over 2. Now I'm only looking for the solutions between 0 and 2 pi, right? I could get all my general solutions and do all that stuff, but just in an effort to reduce our time here, the solutions you would get here would be pi over 2, 0, pi over 2, pi, 3 pi over 2. Those would be the only answers if we were looking between 0 and 2 pi. So we could be 0, but we can't be 2 pi. Those would be the only answers, all right? 0, 0, pi over 2, pi, 3 pi over 2. Yes? Now, I hope that you were taught that when you're working with an equation, if you square both sides of the equation, what must you always do? If you get answers, what must you do? Check them. You have to check them. Because by squaring the equation on both sides, if there is an answer, you're going to find it, but you may also introduce extraneous solutions. So we have to check each one of these because we squared both sides. So let's just check 0 real quick. Up into the very beginning, the first equation we had, actually I'll write it down here. It was sine x plus cosine x is 1. Is it true that if I plug in 0, this is true? So what's sine of 0? 0. What's cosine of 0? 1. So that will check. So this answer works. How about pi over 2? What's sine of pi over 2? 1. What's cosine of pi over 2? 0. 1 plus 0 is 1. That works. How about pi? What's sine of pi? 0. What's cosine of pi? -1. Is -1 equal to 1? No. Throw that one out. How about 3 pi over 2? What's sine of 3 pi over 2? -1. Cosine of 3 pi over 2? 0. -1 does not equal 1. Throw that one out. So we found the 2 solutions. There's 0 and pi over 2. But we also had extraneous ones. So just remember that if you have an equation like this, You are always allowed to square both sides of the equation, but you must investigate the possibility of extraneous solutions. Right? I thought I'd have more time for problems, but I don't. So here's what I'd like for you to look at for your homework. Page 649. Let's see here. $15. 18. 23. 27. 57. 59 and 61. Yeah, that should be good to just get you started. We'll have to come back and we'll have to tie up a couple of things in this section. My goal is on Wednesday to get through 8.6 and 8.7. 8.7 in your book is 1 page. So 8.7 is really short. So we'll finish up Chapter 8 on Wednesday. I think your test will cover only Chapter 8, but I will start Chapter 9 on Monday of next week. Okay, so we're going to start. We have to see law of cosines and law of sines before we leave. Yes? We'll have some review. Yeah, let me work on it. Now that I know we are going to get to the end of 8, let me start putting something together. Huh? Monday will not be a day of full review or anything. We'll probably do like I did last time where what did I do? I gave you a set of problems, right? It'll be similar to that. No, I'll probably do that by the end of the week. I just need to make sure we finish Chapter 8 before I make a review.